I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Chinmay Sonawane is a researcher and PhD candidate in conservation biology at Stanford University. Before coming to Stanford, Chinmay earned a bachelor's degree at Harvard in organismic and evolutionary biology. Chinmay grew up in Brisbane, not to be pronounced Brisbane, right? Brisbane, Australia, where he developed a desire to understand many things, including how megafauna, big critters, contribute to human well-being. Please welcome biologist, ecologist, and Wonderfest Science Envoy from Down Under, Chinmay Sonawane.
Thank you very much for that introduction, Tucker.
Ooh, Tucker. I like it. Tucker.
A few years ago, I found myself in a scene quite similar to this one. I was in a landfill, surrounded by people collecting rubbish. A lot of these workers were actually kids, and even though the kids and I didn't speak the same languages, we'd often play this game together where I'd pick a soccer team and then we'd try and name as many players as we could from that team. Now, one afternoon as we were playing this game, I noticed a young boy approach and join our circle. And as he did so, he bent down, he picked up a half-eaten fruit, and without any hesitation, he took a bite. In that moment, I was so scared for what was going to happen to this boy, because that very landfill we were in was infested with dead animals, with carcasses of cattle, of goats, and of chicken. And this carcass waste was the ideal breeding ground, was the ideal breeding ground for bacterial pathogens. This is the lived reality of tens of millions of people working in landfills. While we in places like California are only indirectly exposed to pathogens and carcass waste and roadkill, tens of millions of people around the world are directly interacting with carcass waste. But there is hope, and that hope lies in the top half of this image. These birds, these avian scavengers, are consuming this carcass waste and removing the breeding ground for these pathogens. And they're not the only animals to be scavenging. We know sharks love to scavenge on whale carcasses. Hippos will happily scavenge. Turtles will scavenge on roadkill, and wild pigs will scavenge practically anything that they can get their hands on. In fact, my colleagues and I got a little curious, so we searched the scientific literature for these vertebrate scavengers, and we found that there's more than 1,300 species of vertebrates that reliably consume carcass waste around the world. Now, these scavengers are really well distributed on our planet. Here's a map of their diversity with yellow and red areas indicating hotspots of scavenger diversity, areas where we see lots of scavenging species. Now, in our search, what we also found was that 36% of these scavengers are threatened or declining in population abundance. And this 36% of scavengers, they are not random either. In fact, there are two characteristics that define the scavenger that's struggling. So here's the first. Here we're looking at the mass distribution of non-threatened scavengers. So along our x-axis, we have mass in pounds, and then the heights of those graphs represent the number of species that weigh that mass. So we see a little peak right around 0.01 pounds. That's telling us that there's quite a number of scavengers that weigh 0.01 pounds. The middle line on this graph is telling us the median mass of these scavengers. So non-threatened scavengers on average are about half a pound. When we look at the distribution for threatened scavengers, what we find is that threatened scavengers are 3 times heavier than non-threatened scavengers. And so that becomes our first characteristic of a struggling scavenger. It's the large scavengers that tend to be threatened. Now here's our second characteristic. Here we're looking at the percentage of facultative scavengers that are not threatened. So a facultative scavenger is a flexible scavenger. They can scavenge or they can hunt. And so animals like wolves, bears, and lions are excellent examples of this. Now, this graph is telling us that 70% of our facultative scavengers are not threatened in the green. In the red, 20% of these facultative flexible scavengers are threatened, while for the remaining 10%, experts don't know their conservation status. Yes?
Can I ask a basic question?
Yes.
What defines a scavenger?
A scavenger is any animal that has a backbone, a vertebrate, that will eat carcass waste, that will eat meat that's already dead.
Versus will eat something that's alive.
Alive, as a hunter. So a facultative scavenger is both a hunter and a scavenger. Okay? But we can have a look at obligate scavengers as well. Obligate scavengers are specialized in scavenging. They can only scavenge, and so vultures are an example of this. And so these proportions that I've showed you are significantly different for obligate scavengers. In fact, half of all of our obligate scavengers are threatened. And that becomes our second characteristic of a struggling scavenger. It's the obligate scavengers that tend to be threatened. To synthesize what we're finding is that these apex scavengers, these large and obligate or specialized scavengers, are struggling. While very importantly, meso-scavengers, our smaller and facultative or flexible scavengers, are having the times of their life in the Anthropocene. So upon seeing this shift from going from apex scavengers who are now declining and now favoring meso-scavengers, we wanted to know why all of this was happening. Why is it that apex scavengers are declining all over the world while meso-scavengers are on the rise? So we dug a little bit deeper into the profiles of each of these scavengers. And what we found was that particular threats to these animals, to these scavengers, kept on popping up again and again. These threats to scavengers included things like fishing and hunting, deforestation and urbanization, and intensive livestock production practices. In fact, these 3 human activities are harming half of all of our scavengers. We also know that these 3 human activities disproportionately harm apex scavengers, the large and obligate scavengers. So, given this decline of apex scavengers, we might now expect there to be less fear in a landscape or a seascape. What I mean by that is when we lose particularly large scavengers, animals like bears or wolves, for example, meso-scavengers, smaller scavengers, might now feel more comfortable to explore the habitat, given that there is less fear of these apex scavengers. We might also expect there to be less competition for carcass waste when there's a decline of apex scavengers. And so we suspect it's a combination of these two factors that enable mesoscavengers to thrive in the Anthropocene. But I would also argue that we, humans, are directly contributing to the success of these mesoscavengers. And that's because we supply them with a lot of food. In fact, when we have a look at the amount of waste that we throw away from livestock every year, we know that this dwarfs the global biomass of all wild land mammals. So if all wild land mammals on Earth died today, this would still be 3 times smaller than just the waste that we throw away from livestock meat every year. To hammer the importance of the food that we provide to mesoscavengers even further, we can have a look at this figure. In this figure, I'm going to take the 1,300 scavengers that we have and group them by the habitats that they're found in. So when you see points up in this top right corner, those are going to represent habitats where scavengers are thriving. They're less threatened and they're increasing in population. Points in this bottom left corner are going to represent habitats where scavengers are struggling. And so here's our data. There's a number of habitats we can have a look at. But today, I'd like to draw your attention to the ones in red. This is introduced vegetation, urban area, anthropogenic habitat, and agricultural land. These 4 habitats are all of our human-dominated habitats. And it's very clear to see that scavengers in these human-dominated habitats are doing much better than the ones in natural habitats in black. We also know that scavengers in human-dominated habitats are smaller. In fact, they're half the mass on average compared to scavengers in natural habitats. All of this really just to say that mesoscavengers are thriving, and they're thriving in human-dominated landscapes, partly due to the food that we provide to them. Okay, thus far I've told you how scavenger communities are changing globally and why that might be the case. But now let's have a look at the consequences for ecosystems and for human health. All of these studies in the red dots show that scavengers from different parts of the world and from different taxa, all of these scavengers are consuming tons and tons of carcass waste. Some of these studies go beyond just documenting this sanitation service. Some of these studies actually quantify the effect of scavenging on the spread of pathogens. So, for example, this study in Malaysia shows that monitor lizards and their scavenging habits actually reduces the abundance of bacterial pathogens, not only in carcass waste, but also on flies that can spread these pathogens to people. These 2 studies in Wyoming and Namibia show that scavenging reduces the spread of anthrax and brucellosis in populations of wild animals. This study in Ethiopia shows that hyena scavenging reduces disease in people. But perhaps most convincingly, this study here shows that the disappearance of vultures in India led to human death rates increasing by 5%. All of this is just evidence that scavengers, particularly apex scavengers, are limiting the spread of pathogens. And I want to be very clear here that mesoscavengers cannot do this as effectively as apex scavengers. studies have repeatedly shown that increasing mesoscavengers cannot functionally replace apex scavengers. In fact, some of these mesoscavengers might be doing direct harm to our health. And that's because some of these mesoscavengers are hosts of disease themselves. So when India lost its vultures, feral dogs took over the role of scavenging. There was a boom in the feral dog population, which then meant tens of millions of more dog bites on people. It also meant tens of thousands of more people dying from rabies. The saddest part about this is that the African continent now is seeing its own collapse of vultures. And people, particularly scientists, have already started to witness and document the replacement of these vultures by feral dogs themselves in a couple of sites. Yes?
Question, are apex scavengers also disease hosts?
They tend not to be, at least relative to mesoscavengers. But if we consider lions to be an apex scavenger, then yes, lions do host some disease as well. The argument we're making here is that mesoscavengers tend to be stronger disease hosts than apex scavengers. Okay, so what does all of this mean for human health? Well, we're seeing a decline of apex scavengers. We expect this will reduce the amount of carcass waste that's removed in an environment and proliferate pathogens. We also expect this to release mesoscavengers associated with disease. I mentioned feral dogs and rabies, but we might expect something similar with wild pigs and rodents, and all of the diseases that these species carry themselves. Both of these are going to increase disease spillover into people. And we know that all of this is being driven by us, by these three human activities. Through this research, we show how these three human activities are harming human health through the pathway in yellow. But previously, others have already shown that these three human activities harm human health through other pathways as well. Ultimately, what we're finding is that the decline of apex scavengers threatens human health. And it particularly threatens the health of those like that little boy that I met at the landfill. Now, none of this research would have been possible without the kind support of these wonderful individuals. And in particular, I'd like to thank and recognize my collaborators, Maya, Natalie, Ariella, Bordan, and Rodolfo. So with that being said, my name is Chinmay Sonawane. I study how wildlife benefit people, and I'd like to thank all of you, Wonderfest and Marin Science Seminar, for hosting this event. Thank you.
Let me ask you, if you can, will you please repeat the questions just
Of
for the
course,
video?
yeah. I think there was a question at the back first.
I was thinking, if you go back in history and look at all the Black Plague or whatever plagues that killed mass amounts of humans in the past, are partly responsible because of this breakdown of scavengers? Is that not related?
It's difficult to say exactly. A lot of these interactions with scavengers happen very early on. It's not something that we can easily trace back.
I know the Black Plague, it was the rats.
That can definitely be a vector that's spreading these diseases. But where did the Black Plague itself come from? Did it come from a carcass that could have been scavenged by, let's say, a vulture? It's tough to say. Hopefully that answers your question. The question, just to repeat it for the camera, was when we see these plagues throughout the last 1,000 or 2,000 years, can these be attributed to the loss of vultures? Yes, a question over here.
When you look at the total caloric load of animal waste,
Mhm.
what fraction is metabolized by, say, a fungus as opposed to one of your scavengers? Because
Mhm.
fungus and bacteria consume a lot of this material.
Yeah. So the question was, when we look at the carcass waste that's in a landscape or a seascape, what percentage or amount of that is consumed by vertebrate scavengers? And for this, I'll just go back to our map of the species diversity of scavengers. If you're in the lab that I'm in, which is the tropical ecology lab, they will very quickly point out that the scavenger diversity in tropical areas is astoundingly low. Typically, this is where we see lots of species, but for scavengers, we're not seeing that diversity. And that's partly because scavengers might find it difficult to scavenge in these habitats where there's a lot of trees, it's tough to see, it might be tough to smell carcasses. There might also be more diseases in the carcasses, so that might pull them away from scavenging. And so this is where I suspect our non-vertebrate scavengers to be removing this waste. Things like invertebrates, fungi, all of these things that aren't, big animals. Again, the point that I want to emphasize is that vertebrate scavengers consume this waste very quickly. And the amount of time that a carcass spends is important, because the more time you give it, the more likely pathogens will proliferate, multiply, and even mutate into more lethal variants. Yes?
Starting from your first slide, where the vultures are going to save us from the rotting animals with pathogens, or save the children, whatever. I was thinking, what about disease resistance in those scavengers? In other words, my first thought was that they must have evolved over time mechanisms to be resistant to many of these pathogens. Otherwise, they wouldn't be scavengers. I mean, it wouldn't have made it that far.
Exactly.
Is there a relation between genetic resistance to certain pathogens and their utility as scavengers?
So the question is whether scavengers that are evolutionarily specialized to scavenge, are they better off in terms of protecting their own health when they're consuming this carcass waste and protecting the health of the environment and people? And so I'll refer to this slide where we're looking at facultative and obligate scavengers. Facultative scavengers are flexible. They hunt and scavenge. Obligate scavengers only scavenge. So as you mentioned, they are specialized for this. There's been thousands, if not millions of years of evolution that have led them to only scavenge. And so medical scientists actually study animals like vultures and hyenas because of their resistance, their immune responses and resistance to particular pathogens that might be in carcass waste.
So that's why the obligate scavengers tend to be not hosts for the. If they were affected by the pathogens and got sick with it, then they would be a host for the transmission.
Exactly. They tend not to host these diseases, and that's why it's so important that we have to conserve these obligate scavengers. They're the ones who are particularly threatened, more so than the facultative scavengers.
But wouldn't the disease threat to the animals be equally strong on the facultative? It doesn't matter if sometimes you catch your own bunny rabbit that's still alive, but if you're going to die from eating a dead one, it doesn't matter if you sometimes eat a live one. It's still, the facultative would still have the same evolutionary drivers to develop disease resistance, would they?
I won't recite that question because it's a little bit difficult to recite, but I will give you evidence to discuss that further. So let's have a look at vultures. When vultures consume carcass waste, a lot of these pathogens might not pass on any sort of disease to the vultures. Now, we can have a look at animals that aren't traditionally considered scavengers, like hippos. If you know the hippo, it doesn't eat meat usually, as far as we know. In fact, it's normally seen eating grass. But there was a really brilliant study that came out, I think, about 10 years ago, that found that hippos, firstly, consume carcass waste much more frequently than we thought. What they also did was that they found in these same areas, we saw mass mortalities of hippo populations. So the suspicion here is that hippos are eating anthrax-infected carcasses. They, as a result, die. This pathogen is then spread to other members of their herd, and that's why you see mass mortalities. That's why it's so important to support obligate or specialized scavengers that are more resistant to picking up disease. Yes?
Couple of questions, and I know others have them too, but I would like to hear how you see we could protect these scavengers. I mean, you talked about the 3 things that we're doing, and like one thing I was wondering if rodenticides are playing a role when we're turning land into farmland and that sort of thing.
So turning what into pesticides?
Turning rodenticides that kill rodents, and then the predators eat the rodents that have died that are their food. So I don't know if there are things like that you're thinking that we could do as a human species to protect these that help us so much.
The question was, what are the conservation actions that we can take to best support these scavengers? One of the things I like about this study is that it documents a global pattern. That's also the weakness of this study. The conclusions we're making are at a global scale. And when you're working in, say, a place like Northern California, things that are happening all over the world might not be as applicable to what's happening here. So conservation actions really should be taken into account the local context as well. But if you're a large organization, you have projects running everywhere, some of the key things that you can do are addressing the 3 human activities that I mentioned: wildlife trade, intensive livestock production, and land use change. Addressing your question on things that we put into our agriculture and how that might be harming scavengers, I'll just bring up the India example because it is the most famous example of vulture loss we have. In the 1990s, people used to see vultures anywhere that they went. In a span of 10, 15 years, Indians could only see vultures in a few selected parts of India. And even there, they were really rare. In fact, vulture populations dropped by 95% in these 10, 15 years. And there's one reason why that happened. It's because livestock farmers were using a drug to treat their livestock. You know, the drug can sometimes treat the cattle, sometimes it won't. When the cattle dies, that drug is still within the system of these cattle. And so when vultures swoop in, they're eating this. You can imagine the sort of effect it might have on their body, particularly given that it's a novel compound that they might not have evolutionarily adapted to take in. So vultures disappeared simply because of a simple practice that we had in livestock production.
Has that been changed in India?
It has been changed, and we're seeing vulture the decline level out, potentially even a slight increase. But there's a very long way to go with recovering these vulture populations.
One more question?
One more question, yes. Yes, please.
There was a program on PBS recently, and I think it was in Finland, and they were talking about the fishing industry, and there was a certain kind of fish that was abundant, and some of the classic ones that everybody loves wasn't abundant. I think it was called dogfish. They were unattractive, but they had really good taste when you cooked them. So they decided, as I think a country, let's see what we can do to stop having so much waste. So they showed a pan with a fish's fillets. Over here was all of the debris from the fish. Everything that was in the fish that would have been dumped. They made a commitment to use every single bit of it. They showed high fashion clothing, sports coats for men, outfits for women, shoes, bags out of the skin of the fish. They got collagen out of the fish, and they made drinks like we buy soda pop that have flavors. It's collagen with a little spin of cherry or lemon or lime, and the kids love it. And they made so many things out of, and the collagen tissue they use for surgeries for people, so they could wrap it around bodies, administer medicine, put it inside their bodies with the collagen, and on, all of these things, so they didn't just go and dump it away. For everything in the country, they're looking at it with a new lens.
That's an excellent example of sustainably using everything that we collect. Yeah. I mentioned the amount of waste that we throw away from livestock meat. It's estimated around 70 million tons. We also know that from fishery discards, there's about 5 to 10 million tons of that just being thrown out into the ocean. So there's a long way to go before we can use everything.
No, I know, that's true.
Animals are eating this. Yeah.
Scavengers.
Thank you, Chinmay.
Thank you so much. I appreciate it.
Escape? Yeah. I've got to get myself a dogfish sport coat. Got it.
You should Google that.
Bethany Suter is a researcher and PhD candidate in the physics department at UC Berkeley. Before coming to Cal, go Bears, Bethany earned her bachelor's degree in physics at the California Institute of Technology. But at Cal, go Bears, Bethany studies high-energy particle physics beyond what is called the standard model of particles and fields. Dark matter is certainly, I think we're now quite certain, beyond the standard model. So we're going to be thrilled, I think, to learn about new ways to detect dark matter in the laboratory instead of having to look cosmically. Please welcome physicist and Wonderfest Science Envoy, Bethany Suter.
Thank you so much for that introduction, Tucker. And I'm very excited to be here with you today and share some of my research. Today I'm going to be talking to you about the direct detection of dark matter. So, just to give you a little bit of a perspective on what the universe is made of, we have this pie chart here. It shows us that 73% of the universe is going to consist of dark energy, which is a very unknown form of matter that we still need to do a lot more analysis about. Then 4.6% of the universe is everything we are used to seeing. So you and me here in HopMonk Novato, and the planets, the stars, pretty much everything we know that exists. And then 22%, we don't know exactly what it is yet, but we're well on the way of figuring out. And so that 22% is dark matter, which we're going to analyze a little bit more today. All right, so as a bit of an outline of what we're going to discuss today, we're first going to start by looking at the evidence for dark matter. We're then going to move on to thinking a little bit about what dark matter actually can consist of. And then finally, we're going to look at how we're actually trying to detect dark matter today. So first of all, why do we think there is dark matter? So there is an abundance of evidence for dark matter. However, unfortunately, I only have 20 minutes, so we're just going to go through three of these today. We're going to look at galaxy rotation curves, gravitational lensing, and the bullet cluster. All right, so first, galaxy rotation curves. So let me just situate you here a little bit. So today we're looking at the spiral galaxy Messier 33, and we have this lovely picture of it. And we've overlaid a graph on top of this to kind of show you a little bit of data about this galaxy. So specifically, if you look at the x-axis, you are looking at the distance that you are from the center of this galaxy. And this is in light years, which is the amount of distance that light would travel in a year. So that's a very large distance. And then on the y-axis, we're looking at the velocity of the stars that exist at each specific radius that are going around this galaxy. And what we can see is that there are two different curves plotted here on this graph. And the first curve is the expected velocities, the velocities that you would expect these stars to move at. And you can get this curve by looking at Newtonian gravity, which maybe some of you had a high school physics class where you encountered the classic equation, the force of gravity is equal to g m squared over r cubed, or r squared. And you can do this a little bit of math and figure out that once you get outside of the main bulk of the galaxy, you'd expect the velocity of the stars to dramatically increase because they're no longer feeling the tug of gravity nearly as strong due to that diminishing of 1 over r.
Dramatically decrease.
Yes, they decrease. However, when we actually take the data, these are real data points from this specific galaxy, we don't see that decrease in the velocity. Instead, the velocity kind of flattens out and almost increases as we go farther and farther away from the galaxy. And so this implies to us that our description of the galaxy, just using the visible matter that we see through this picture, is just an incomplete description. And so there has to be some sort of matter that is invisible and we can't see it. And we've chosen to call this matter dark matter. So that's galaxy rotation curves. The next thing I'm going to talk to you about is gravitational lensing. So gravitational lensing occurs when you have two different objects that you're going to be looking at. So first you're going to be looking at a galaxy that's very far away, and then you're going to have some large, massive object that is somewhat in between that galaxy and us. And I have this diagram here that kind of shows this going on. And so we actually know from general relativity that if you have a large amount of matter located in an area, that's actually going to bend the space-time. And since the space-time itself is bent, as you can see from this fabric of space-time picture, these light rays actually get bent as they're traveling towards Earth. So although they're traveling according to the path that they need to travel to get to Earth, they are traveling on a curved path. But we on Earth don't actually see the universe as necessarily being curved. So if we, on the other hand, are looking out, we just see these rays kind of traveling back in a straight line backwards. And so what ends up happening then is we get exactly this picture here. So this is a galaxy, a spiral galaxy, that has been smeared out in an almost complete ring due to the presence of this very massive object in the center. So this lovely picture is known as the Einstein ring because it's an excellent demonstration of general relativity. But it turns out this is also actually an excellent demonstration of dark matter because we can look for the effect of gravitational lensing across the universe on very large galactic scales, and we can see small distortions in the light coming to all of the galaxies from the universe to us. And that gives us a very good estimation of the matter that exists in the universe that light is traveling through. And what ends up happening then is we can figure out that amount of matter, and we also have the matter from the visible light that we see. And if we put those two numbers together, again, those numbers just do not align. And so this again predicts that there must be some source of invisible matter, dark matter, that we don't see. All right, the final evidence we're going to look at today is the bullet cluster. So the bullet cluster is a very iconic picture that we've found, or galaxies that we've found in the universe, where, recently speaking, cosmologically scales, there are two galaxies that have just collided and gone past each other. And we can look at these two galaxies in kind of two different ways. The first we can look at using the tool of gravitational lensing, which I just discussed. And what we can see with gravitational lensing is we have two main distributions of where matter is in these galaxies. If you want to figure out how to read this graph, it's kind of similar to like a topological or topographical map of heights. So the more circles you're inside, that means there's more matter concentrated in that region. So we can see there are two main distributions of matter. However, we can also look at it using just the visible light. And what we see in this picture is that actually the matter is not concentrated in these regimes where gravitational lensing tells us, at least the visible matter is not, but instead it's actually much more in this central region. And so again, we see the presence of matter that is not where we see it. So must be some matter here and here that is just not visible to our telescopes. And so this in the end is our final evidence for dark matter that we're going to cover today. Okay, so moving on. So we know dark matter exists, but what actually is it? Well, in essence, we don't actually know, but there are a lot of things we have figured out about dark matter at this point. So for instance, we know that it is dark. That means it doesn't emit light, doesn't interact with light in any way. It interacts only weakly with forces besides gravity. We also know that it's cold, which means that it's very slow. It's not moving very fast, at least compared to the speed of light. We know that it's collisionless, so that means it doesn't interact with itself on large scales or with other particles as well. So it doesn't actually interact with us as humans very much either. It's also stable. We still see a lot of it around us today, which means that it had to have been created, sometime in the early universe and still exists today. So it's long-lived. And finally, it's abundant. It makes up 5/6 of matter, ignoring dark energy. And so this is a really big piece of the universe that we don't completely understand yet. And so those are the things we do know about dark matter, but there is the main thing that physicists really want to know and have not yet figured out, which is the mass scale of the dark matter. And so, physicists have been working very hard to try to figure out, okay, what mass scale could the dark matter be at? And they have put a lot of limits and constraints on what this dark matter mass could be. However, there is still a very large window of dark matter masses that could still possibly exist and be populated by a large variety of different models. And so, just to give you a little bit of perspective of how large this mass scale is, it goes from 10 to the negative 22 eV, which is 1 octillionth the mass of the electron, which is already an incredibly tiny particle, all the way up to 10 solar masses, so 10 times the mass of the sun. Now, this may sound absolutely terrifying because that's way too much parameter space to look for, but what we have figured out is that there's actually constraints on what kind of model you can have in each of these different regions. So these different colors kind of correspond to models that act very differently. And the methods that we're going to use to try to detect them would also look very different in those different regimes. Unfortunately, again, I don't have enough time to go through all of these models in detail. So today, we're just going to be focusing on a model that exists in this little smaller mass regime. So right around the mass of the other fundamental particles that we know of, so protons or electrons, somewhere in that regime. And this kind of makes sense because that is the mass scale that we have seen for other fundamental particles. So we have some prior understanding that maybe dark matter would be in that regime. All right, so that explains what could dark matter be, or doesn't really explain it. So now let's talk about strategies for trying to detect this dark matter. All right, so the first thing that I want to do in this section is I'm actually going to try to do a Fermi problem with you all. And this requires you all to give me a little bit of feedback back. So hopefully I've prepared you well enough for going through this. If you've never heard of a Fermi problem before, this is when you are trying to do like a back of the envelope calculation or an order of magnitude calculation, where you don't have like exact numbers or exact formulas to try to get an answer, but you're still going to put those numbers together, what you can guess, and figure out, okay, this is an approximate number that seems to be about right. If you want, I don't have, you can look up the actual origin and why it's called a Fermi problem. It's a little bit of a sad story because it relates to the nuclear bomb, but it's also a good one, so feel free to look it up. So, the first question I'm going to ask you all is, does anyone have any idea what the surface area of a human is? What is it? 2 squared meters. So we're going to look for feet squared, just because that's maybe a unit that non-scientists are a little bit more interested in. But we're a physicist, so we're going to do an approximation. In physics, there's always the notion of if you can make anything a sphere or a cylinder, then the problems often become a lot simpler. And so in this case, we're going to assume a cylindrical human. So, say a human is about 6 foot tall. It's a little bit more than probably most humans are, but about, for a round number, maybe 8 inches in radius. That leads us to about 25 feet squared, which I think is about the right number. Or, in a little bit more fun units, it's about the area of 32 medium-sized pizzas, which is a lot larger than I thought it would be. All right, the next question is, how massive is dark matter? Anyone tell me?
It's 25% of the universe.
It is 25% of the universe. Well, it turns out this is a little bit of a trick question. As we just talked about, we don't know. However, as I said before, we're going to be talking about things that are in the regime of other particles that we currently know of. And so we're going to say about 100 GeV.
So not the mass of all dark matter, the mass of a particle of dark matter.
Yes, specifically, sorry, should have clarified. How massive is one particle of dark matter? And for better units, this is about 100 times the mass of the proton. All right, the next question is, does anyone have any idea how fast dark matter is moving near us? I don't expect you all to necessarily know this one, but I gave you all a hint. Do you remember one word that is associated with it? Yeah. Slow, exactly. But I did clarify that that's slow compared to the speed of light, which is extremely fast. So it turns out that the dark matter moving near us is about the escape velocity of the Milky Way galaxy, which is 18.5 miles per second, or like traveling from HopMonk, Novato to New York City in just under 3 minutes. So actually quite fast. All right, and the final question, which I did not give you all any hints about, so I'm just gonna kind of give you the answer because we need it, is how dense is the dark matter around us? So this is kind of the question that you were answering a little bit more before. And so it turns out this is about density of 0.3 GeV per centimeters cubed, or about 10 to the 20 times less dense than helium gas, which we know of as an extremely light substance. So this is very not dense. So we can put all of these numbers together, and what we get is the number of dark matter particles going through us each second, with the formula described right here, if you are interested. And what this tells us is that 200 million dark matter particles may pass through your body every second, which is an insane number of dark matter particles, right? However, I do want to say the caveat, this is a very dark matter mass, each individual particle dependent answer. So if the mass of the dark matter actually ends up being much larger than what we were just assuming, you wouldn't necessarily expect 200 million sun-sized dark matter particles to go through your body every second. That would probably kill you, even if they don't interact a ton. So, if we do have 200 million dark matter particles streaming through us each second, that leaves us with the question, okay, can we actually detect those particles? And turns out physicists have been working real hard to try to do this for about 40 years now. However, the main issue is that even though there are so many particles that are, passing through us, they interact almost not at all with us. And that means they're not actually hurting us when they fall through, or they pass through us as well, but it means that detecting them is very challenging. So, what physicists have figured out is that there are actually some materials, such as xenon, that are very dense, and that actually increases the chance that the dark matter is going to interact with the material. So physicists have figured out that if they get large vats of xenon and put detectors around them, then if the dark matter comes in, and on the small chance that it interacts, it might emit some sort of light or other particles such as electrons that could then be detected in these detectors while the dark matter goes on its merry way. And we'd be able to see that and be like, aha, we know what dark matter is now, we've found it. However, unfortunately, we've been looking for dark matter since 1985, and we've seen absolutely nothing. So, however, one of the things that is interesting is that these searches have been primarily limited to a very small mass regime at this point. And so one of the things that the physics community that I'm very much involved with has been trying for the last 10 years or so is how can we try to expand that mass regime? How can we actually probe more than just the small window that I was talking about, but actually go through this entire span of masses? So how can we do better? Oh, also, just to give you an estimation of how large these tanks have gotten, this is a human, and this is the tank that I was showing before. So these are extremely massive experiments at this point. So this gets us to my actual research, where we're introducing the idea of phonons. And so this is kind of showing, so these two diagrams are showing you the experiments that have been happening in the past on the left, yes, I can do directions, and the new experiments that we are proposing on the right. And so on the left, we again have the dark matter coming in, interacting with a single nuclei, or one atom essentially, and then going off and it emits some light or electrons that we can then detect. However, this actually only works for somewhat larger masses of dark matter, still very small and not at all close to the solar masses, but something along the same scale as the actual atoms that they're interacting with. However, if we want to try to probe these smaller masses, we actually need a different technique, because when the dark matter comes in, it actually ends up being a little wavy as it comes in. So I don't know if you all have heard anything about the particle wave duality, but essentially if you have really small particles, even smaller than perhaps these ones, they're actually going to act much more like a wave as they're traveling through the medium as compared to being a particle. And if you want to ask questions about that, we can talk about it more later. But what happens is if that wave is wavy enough, when it comes in, it's not just going to interact with one nuclei anymore. It's actually going to interact with the entire crystal. And when that happens, it's going to cause something called a phonon. And so you can actually think of this, if you want to envision a cube of jello that you flick, then when you have this cube of jello, it's going to like vibrate, right? Like you're going to see wave ripples going through the thing of jello. And it's exactly the same concept here, just on a much, much smaller scale, where when the dark matter comes in, it's actually acting to hit like the entire piece of jello, which is now our crystal, and cause oscillations in that jello. And so when that happens, you're going to get basically regions of the crystal or jello that are like less occupied by atoms and regions that are more occupied by atoms. And those are actually those like regions are gonna move through the crystal in a coherent fashion, which basically means they're gonna move like at the same rate together. And if you put those together, that is what's called a phonon. Because we just talked about particle wave duality, where if you have a wave, if you have a particle, it can act like a wave sometimes. Well, it turns out if you have a wave in a material, it can actually act like a particle sometimes, going the opposite direction. And so it turns out that it's very useful to think about these waves in this crystal or jello or crystal of being something like a particle that is actually interacting with the dark matter. So what happens is when we're looking for these particles, dark matter particles in this lower mass regime, we're actually going to need experiments that are looking for these objects' phonons, which are those particles, as compared to just looking for light or electricity that are released from a single dark matter particle interacting with the material. So just as a little blurb about my specific research that's like editing this viewpoint a little bit. So we're going to do two changes. So when the dark matter comes in, we're not just going to assume that one phonon comes out, but we're also going to assume that multiple phonons come out. So basically, there are going to be multiple vibrations going through the material that we can now detect. And this is a little bit easier to detect than just one vibration. So this is a nice thing for us. It's for experimentalists who maybe don't have equipment that can get to quite the sensitivity that they need to just detect one. The other thing that we're interested in looking at is if we include spin-dependent interactions. So spin is an intrinsic angular momentum of particles, where basically, even if you completely slow down a particle, and such as not visibly moving at all, it turns out that it actually still has an intrinsic angular momentum. And this changes, like, depending on what that is, it'll dramatically change how that particle interacts with the universe. So if our dark matter also has this intrinsic angular momentum, there's a possibility that it might interact with the material in a slightly different way. So my research has been trying to analyze, okay, how does the rate of interaction kind of change depending on whether we are interacting with spin or just interacting with the mass of these atoms. All right, I hope I didn't lose you completely on this last slide. I know it's a little bit more technical than some of the other ones, but I wanted to add in a little bit blurb about my own specific research. But in conclusion, the evidence for dark matter is super strong at this point, ranging from galaxy rotation curves to the bullet cluster. And these gravitational observations tell us that dark matter makes up 85% of the matter in our universe, and yet right now we don't know what it is. And so physicists have been looking for dark matter here on Earth for over 40 years, and we haven't found it yet. But a lot of people think we might be on the cusp of a breakthrough. You know, any day now, maybe we're going to detect it. And my hope is that possibly these novel techniques via phonons might be the way we do it. All right, any questions? Yes?
So my conclusion from the lensing is that the dark matter is not evenly distributed, but it's also concentrated potentially in places that the rest of the matter is.
Yeah, exactly.
But
So
not quite identically from the bullet cluster. They're not in the bullet cluster. The dark matter is a little farther apart than the light matter.
yeah, so the question is, in general, we think of dark matter as usually being distributed maybe a little bit unevenly, maybe like closer together, more densely around like galaxies or things that exist. But then the additional part was that in the bullet cluster, we don't actually see those distributions being the same. And so that's actually a really good point. So let me go back to that picture so we can see it together. So in this case, the reason why this has happened is because of how dark matter doesn't really interact with the other matter. And so what happens is, originally you would expect to have those two, the visible matter and the dark matter that we see, be like tightly overlapping, like more dense at the same locations. However, in the interaction, what we see is that most of the visible matter that the galaxy is made up of is actually going to be in like gases and plasma. And when those collide, they actually collide. They interact a ton. And so they kind of just get caught in the center here. But dark matter doesn't see the other matter, doesn't interact with it. So it just flies right through. And so we expect to get this displacement due to this effect. Yeah?
You mentioned that this dark matter might be 85% of all known matter. Do calculations from these three ways of determining its existence, do they give you similar ballpark ratios?
Yeah, so they do. They actually match up quite well. Obviously, there is some discrepancy, but those discrepancies are within the amount of error in those calculations themselves. So they do match up quite well. Yeah.
Has anybody considered, the Newtonian physics at one point was a revolution, and then quantum physics was a revolution? Has anybody, I'm sure people have considered that there may be something going on in the math.
Yeah, absolutely.
Yeah.
So that actually comes back to the bullet cluster itself as well. So the idea that you're suggesting is an idea of modified gravity that could maybe account for this different mass, like the distributions that we're seeing compared to gravitational lensing, which is purely gravitational, versus visible light, which we're obviously seeing through other methods. However, in general, when we think of gravity, it would completely, utterly transform how we think of gravity if gravity doesn't come from matter. And specifically, it has, in this picture, if it's not coming from the visible matter, it's off-center. Or sorry, if it is coming from the visible matter, it's off-center from that, which means you no longer have this ability to be like, oh yes, the gravity is clearly affecting, the surrounding area. Yeah, so in essence, this is actually one of the best proofs for, or reasons why we don't think it's a modified gravity scenario, because the distributions just don't line up quite right. There are some people who still think that a modified gravity scenario is maybe by Occam's razor a more simpler explanation, but the vast majority of the field has come to the conclusion from this and other calculations that that's probably not the case.
No graviton has ever been detected, right?
No graviton has ever been detected. It would probably be either massless or just so incredibly tiny of a mass that it'd just be very difficult to detect. Gravity is a very weak force compared to all of the other forces that we're aware of, and so the other interactions would just kind of drown out that under most cases. And also, even if there is a graviton, that still doesn't exactly explain this because of this off-center effect, right? You still would want the gravitons to be coming from matter themselves and having gravity interact with matter. So,
Last question.
Yeah, last question. Yes.
So when you say dark matter, I immediately thought when you showed the wavy graph, I immediately thought of radio transmissions, because really it's if you have radio transmissions, it flows in a certain pattern, in a wave pattern. How does radio transmissions, for example, affect the movement of dark matter if there is something called interference?
That is a good question. So there are radio telescopes that are actually looking for dark matter as well, because that's one of the ways we can probe the universe. I don't know specifically about interference. That's going to be very dependent on which specific dark matter model that you're going to be looking for. But that's actually a really interesting question. Yeah.
All right, Bethany, thank you. All right, our third presentation. S.Waterton is a researcher and PhD candidate in biochemistry at Stanford. Sean grew up in Alexandria, Virginia. He earned a bachelor's degree in chemistry at Cornell and a master's in biochemistry and molecular biology at Georgetown University. Sean also spent 2 years You've been around. 2 years at MIT, helping to develop a novel single-cell RNA sequencing technique. Please welcome biochemist and Wonderfest Science Envoy, S.Waterton.
Can everyone hear me? It's good. Awesome. So my name is S.Waterton. I'm a 4th year, soon to be 5th year student in the ND lab in bioengineering, surprisingly. I left my home program and joined another lab. And today I'll be talking about engineering the future in electrical energy, power, and molecular production in yeast. So typically, we don't really think about producing molecules in different organisms, but there are a variety of medicines and food products even that you can use a live organism to create. Right? And so yeast is one of these models. The same yeast that you use to rise bread is also used in the pharmaceutical setting to produce medicines, to synthesize fuels, and at home you can make beer and bread with them, and you can grow it and create yeast extract and whatnot. But the question really is can we start to use electricity to kind of enhance the ability of yeast to produce these products? And I'm going to spend a little bit of time today talking about why we want to do that, why that's interesting, and whether or not this is feasible or possible or really helpful. So to start off, I'm going to ask you all a few questions. I'm going to turn this on you. So this is a picture. This is a historical picture, actually. And so does anyone have any guesses for what they're doing in this photo or why these people are laying here? Sorry for the risque photo.
Artificial sun?
That's great. That's actually perfect. That's exactly what it is. That's good, yeah. Oh, sorry.
Can you repeat the answer?
It was artificial sun. So the reason is, it's a little bit difficult to see, but up here is a light. It's a UV lamp. Where you can see these people are not very clothed, but they do have protection around their eyes. And then the reason is that this UV lamp is used to illuminate them because, when you're in a dark space for a long time, your body isn't producing enough vitamin D. And so one of the therapies that you can do is actually to expose people's skin to this UV lamp, and it'll help the body produce vitamin D. So what you see here is this man in this uniform kind of administering this therapy. Now, I'm going to give you a little bit more historical context here. Can you tell me, this photo was taken in the late 1930s, 1938, 39, in France. And it was inside the Maginot Line. I don't know if I'm pronouncing that correctly, the Maginot Line. Which is this extensive defensive fortification built between the border of Germany and France. So can anyone tell me, hopefully this is straightforward, what they were doing there, why they were preparing, or what they were preparing for inside this line? So
Avoid World War II.
there you go. Exactly. So Maginot Line is this extensive defensive fortification built between Germany and France. And what the French did after World War I was they said, this is Germany, they invaded along these lines. We're going to build defensive fortifications along the routes that they invaded, right? And so they looked at the mistakes that they had made in the previous war, and they spent a ton of effort trying to build these protections to prevent the mistakes that they had made in the past. And so what we see is one of the results of that. They're testing this UV therapy because when you're inside this big concrete fortress for extended periods of time, you aren't exposed to the sun, and so the wanted treatment for vitamin D deficiency. So, historical question, does anyone know how the war went for France in World War II? Not great. France formally declared war on Germany in 1939, somewhere around September, and for about 7 months there was no war, no bloodshed. And then Germany invaded, and in less than 3 months, France had been conquered, and they were occupied by Germany for the rest of the war.
Sean, so first though, France declared war on Germany.
Yes.
Wow.
So Germany invaded the surrounding countries. So when they built the Maginot Line, actually, they only built it along the border of Germany and France. But if Germany invaded the country, connected France, just go in by avoiding the wall. And so that's exactly what happened. And Germany invaded the country adjacent to them, and then walked right into France and took it over. So there's a lot of writings about this piece. France was seen as a world power, and it was really shocking to the world that they were taken over, and not just taken over, but taken over so quickly. And so there's this one historian, Mark Bloch, who wrote a book that was titled, translated, it was titled Strange Defeat. And what he says about this is, what drove our armies to disaster was the cumulative effect of a great number of different mistakes. One glaring characteristic is, however, common to them all. Our leaders were incapable of thinking in terms of a new war. Now, Carol Fink, another historian, tried to explain further what she thought Bloch was saying in this quote. And so she says, Bloch blamed the ruling class, the military, the politicians, the press, the teachers, for a flawed national policy and a weak defense against the Nazi menace. Germany had won because its leaders had better understood the methods and psychology of modern combat. So, what's clear in these quotes is what they're blaming is France's inability to adapt to new changes in technology. The way the world was fought in light of these new changes in technology. They spent their time playing whack-a-mole, really, with the mistakes of the previous war, and built these defensive lines just trying to fix the mistakes of the past without really accounting for the future. And so the reason that I show this photo is that I want to talk about how we can start engineering, not for the world as technology currently exists, but how we can start to think about how technology will advance and how research needs to advance along with it, adapt to the technology that's being shown. So, it's a little bit difficult to see the slides, but one thing that we can start to do is to look at trends in technology, current trends. And so one current trend that's interesting to me is the growth of photovoltaics. Photovoltaics are being built at this really accelerated rate across the world. And so what I have in this graph, which you'll see in a second, is the total global solar installations around the world. Along the x-axis, what you see is each year represented. So this would be 2007, 8, 9, 10, going up until 2013 when this report was published. And on the y-axis, what you see is the capacity of those solar panels in gigawatts. How much energy can be converted from sunlight into electricity. The total capacity of the solar panels built in that year. So in each column, what you see is the amount of new solar installations globally for that year, right? So 2010, you see 18 gigawatts were installed. 2011, what you see is 29 gigawatts were installed, so new solar panels. And so if you wanted to look at the total global installations, you would actually have to sum all of the amount of installations up until that point, right? So this is new. And what you see here is that as time goes on, people are installing more solar panels, but they're actually accelerating the rate that they're installing these solar panels. And so this is really incredible. What you see around the world is that we're just building at this increasing rate of solar panels. And what you see is, when you look at the total amount of photovoltaic capacity in the world, it's actually doubling every 2 to 4 years, right? And so what they also did was projections. And so they projected that this rate would only continue to increase. Now, what's funny is, this is already off. China alone reported that it built about 700 gigawatts of solar panels capacity in 2014. Not in the full year, between January and August of 2024. And so these projections even are lowballing it for the amount of solar panels that we're really building. And so what we're really pushing ourselves into, and what we're really seeing how the world transition into, is this world where we're able to capture solar energy and convert it to electricity at a rate that's never really been seen before. Now, a little bit of additional context is that the world's global energy usage for electricity specifically is about 800 gigawatts. And so what we're seeing is China, we're talking purely about capacity, not about actual implementation, but capacity to generate electricity. So China has built enough solar panels to do that in a single year. There's a lot of nuance there that I won't get into, but about the implementation of solar panels and implementation of the energy usage that prevents it from working out that clearly. Storage is the major issue, and so we can generate a ton of electricity and there's just nowhere for it to go. But when we're talking purely about the capacity to generate energy, we're seeing the world enter this real new age. And so one thing that I also want to talk about is giving some context relative to the other energy generation techniques, the other ways that we generate energy in the world. And so this is a report from the DOE in the United States. It's looking at the energy generation in the United States. So what you see before 2020, is real numbers, right? These are not predictions, these are real numbers looking at the amount of energy that is used and the source of that energy, right? So you can see is storage is right here, but photovoltaics, storage isn't actually an energy generation technique, it's a means of comparing how much electrical energy we can store. But photovoltaics is how much energy we're actually producing. Wind produces some amount, hydro, geo, ENG is natural gas, and there's different ways that you can process natural gas, and you have coal and nuclear here. So what I really want to highlight here is how right now, photovoltaic energy is a fairly small fraction of the amount of energy we can generate, but as we move on to the future, the prediction is that photovoltaics will start to overtake all of the other energy generation techniques, and it will form the majority of the energy that we get. And so when we're starting to think about research practices and research, the direction of research, we really need to be considering where we're going to be getting the resources in the future. And so my professor saw this and he came to me and he said, Sean, I think that we should start to look into trying to look at using electrical energy to do the processes that we already do, and to try to see if we can start rewiring or coming up, MacGyvering some new techniques to start to use electricity for processes that are already happening. And so we had this talk, can we start to rethink how we use electricity? And if you look outside, I'm sure you've seen an electric car driving around the road, you can see that these processes are already kind of being implemented, right? We're using electric cars to kind of replace gasoline-powered cars, but we're wondering, can we take it further? What are the things that we can start to do with this? And so, what I want to talk about actually is the use of electricity to grow food. And so, we can actually look, there's a paper that was written in 2021 that looked at the theoretical efficiency of growing microbes using solar panels, energy from solar panels, electricity. And they compared it to traditional agriculture. And so this is what you're going to see on the screen. What you see on the left is the protein that you can get from 1 hectare, can't pronounce that, of soybean. So 10,000 square meters of soybean. And what you see is that it produces about 1.1 tons of protein per year, right? Which is enough to satisfy about 40 people per year, right? And what you can do is you can imagine just comparing the land use efficiency, that same area, that same plot of land, but covered in solar panels. And what you see here is the distribution of how that energy is used to grow microbes using electricity and CO2 from the atmosphere. And so what you see is about 66% of this electrochemical energy is used. Sunlight hits, you harvest the electricity, and you use it to create feedstock for these microbes that can grow off of different chemicals. About 9.3% of it is used to harvest CO2 from the atmosphere. So there's ways that you can take CO2 from the atmosphere and concentrate it to make these reactions go a little bit faster. And you can use electrical energy to create different chemicals, different products that you can use to feed these microbes. Now about 24.2% of that energy is actually just used in the different processes to grow the microbes. So you have to heat the media that these microbes will grow in, you have to stir it to allow proper growth. But what you see at the end of it is about 15 tons of protein per year using the same amount of land, same amount of sunlight hitting that land by using this electrochemical growth. And that's enough to feed about 13 times more people when we're talking only about the protein. Now, when we're talking about pure calories, the numbers aren't as pretty. You can get 2 to 4 times more calories by covering the same amount of land. I think protein was selected because it's the prettiest. But the point remains that using electrically grown microbes, you can actually produce these much more efficiently. So now we've shown that the theory says that we can produce food at rates and efficiencies that are much higher using electricity. But what I was interested in and what I want to do with my thesis is to use electricity to produce specific molecules. So I mentioned at the beginning of my PowerPoint that yeast is often used to produce medicines. For instance, insulin, it can be produced in yeast. You can put the gene for insulin into yeast, grow it up, and then harvest out the insulin. But I'm looking in my thesis for ways to tie electrical energy into some kind of chemical that you can provide to yeast to produce medicines or biofuels, or even stimulate the growth of yeast from electrical energy and CO2 as the main sources. And so that's what I'm looking to do. The intermediate that I'm specifically looking at is something that can be used to grow yeast. It's acetyl-CoA. It's this intermediate that's used both in the production of these long chain fuels and can be used to grow yeast itself. But I didn't include the pathway here because it gets too in the nitty-gritty of things. But if you're curious, please ask. I'd love to talk about it. So finally, I'm getting back to this picture of the Maginot Line, and one of the reasons that I put this picture up was because I wanted to talk a little bit about the mistakes that come with only trying to solve problems by fixing mistakes. And one of the things that my professor talked to me about when he first started was actually not about the chemistry at all. He didn't actually mention the chemistry. What he said was that this electricity growth this electricity generation ability was rising very quickly, and it was an opportunity. And one of the things that attracted me to this project and eventually to this lab was the idea that he wasn't really interested in research that's aimed at fixing problems. Right? There's a lot of problems with existing research, and a lot of research really aims at trying to take those mistakes that are known and design fixes for them to improve current processes. But he didn't care about that at all. What he really cared about was possibilities and the implications of research that didn't really exist yet. And so when I talked to him, this is the slides. These are the slides that he showed me actually. He says, implications for the future, ubiquitous production. One of the beautiful things about using sunlight and air as the source for production of molecules is that sunlight and air are ubiquitous. You get them everywhere. Top of a mountain, middle of the ocean, just floating on a boat. It doesn't matter where you are. And so you're able to produce molecules, in places with little to no water, poor soil, and minimal plant life. And this really struck me because it really changes fundamentally the way that we think about the world, right? So much of the world's assumptions are in resources being allocated in certain locations in the world. We dig oil in one place and have to ship it to another place, right? When you're traveling on a plane, fuels becomes very important because fuel has weight, right? So you need a certain energy density relative to the mass of the fuel, right? But these things change when you start to think about production ubiquitously. When energy is provided through sunlight and through air, and you have the chemical reactions that can happen quick enough to create molecules of interest, you don't have to think about those kinds of things anymore, right? From the military's perspective, a lot of funding comes from the military, so it forces me to think about this. From the military's perspective, it means that you can imagine a truck that drives and has the ability to produce enough food for a soldier from just sunlight and air, right? You have eliminated the need for supply lines. Right, when the vaccine first came out, all this research came out, and people found the vaccine, one of the biggest problems wasn't just production, right? Production was limited to factories, but one of the biggest problems was storage. We could produce enough vaccines, but we couldn't store all of it in cold locations. But that changes if we're able to produce everywhere, right? The cool thing about a vaccine is that it can be made by any organism, and so you can imagine a vaccine that's just placed in the yeast that you use to rise your bread, and can produce enough vaccine for you at home. And so what he really was talking to me about was this delocalized production, this ability to produce molecules anywhere at any time. And he thinks there's this fundamental shift in the way the world operates if we're able to do that. And so what I really wanted from this project was to be able to build pathways that happen robustly enough and quickly enough that we could start to rethink the way the world produces molecules. And that's all for today. Thank you all. Are there any questions? Yes.
I saw a talk many years ago where they looked at the membranes, and the membrane is 10 microns across, and so if you put a voltage across a bunch of cells, you get this enormous potential difference across this very narrow membrane.
Yeah.
When you use an alternating current, you can induce channels in the membrane wall to produce whatever you wanted by just having an alternating current across the whole field. Is that what you're trying to do, or are you trying to do chemistry based on it?
Yeah, so what I think you're talking about is membrane potentials and their use in biology. So within an organism, within a cell, oftentimes there are differences in the electrical potential energy, and so you can use that to move specific ions across membranes, and the cell actually uses that to provide energy. right? It maintains this difference in, there's hydrogen ions that can flow into a membrane, and it uses the spontaneity, the flowing of these ions to do various cellular processes. So that's one way that biology uses electrical differences. What I'm talking about is a little bit different. What I want to do is to take electrical energy that's provided through sunlight and find ways to get the cell to either synthesize molecules that the cells can use or directly provide that electricity to the cells themselves. It's a little bit confusing, but one example that I can give is photosynthesis. So I think for most people, we typically think of photosynthesis as you have this potted plant and it grows, and if you put this plant on the windowsill, it has access to sunlight, it grows. As long as sunlight hits it, it can grow. But I'm going to ask you to take one step with me further and to look at the molecular mechanism. What actually happens when a photon of light hits a plant is that there are specific molecules within the plant, within the chloroplast, that can absorb light. Very few molecules can actually interact with light, but plants have found heme molecule that's able to absorb light. And what makes this molecule special is that it can absorb light, and it can excite itself to an energy state where it's this excited molecule, but then that excited energy state lasts long enough to actually do a chemical reaction. And so the magic of photosynthesis really is that stability, right? You can have this molecule accept energy from light, and then it can convert it to chemical energy via a chemical reaction. And so the research that I'm really looking at is trying to use electrical energy to do a similar thing. What are the processes that allow us to take this high amount of electrical energy and then create some kind of chemical that the cell can use downstream? And so one example is in an electric field cell, you can have two metal rods, and if you provide a voltage to the cell in the right conditions, you can actually induce chemical reactions. And so the idea here would be to take CO2 as one of the input reagents and produce one energized reagent, that the energized chemical formate, that the cell can accept. You can actually do that repeatedly. You can actually create acetic acid from CO2. You can create, we've gotten up to isobutanol, so it's a 4-carbon alcohol. People are working on expanding it, but for now it seems like formate is the best way to go. But yeah, what I'm interested in is that mix between electrosynthesis and biology. Did that answer your question? Is that?
Yeah. So going back to slide number 6 regarding the soybean plantation, wherein you made you see the potential of, okay, so we're gonna use we're gonna cover. Are you looking at covering the entire soybean plantation with solar panels? Is that what you're looking at?
Yeah, so what I'm doing is I'm comparing just like land area use. And so what this study did is you can actually, what we're trying to do is we're just comparing the amount of sunlight that hits an area and what you can do downstream from that sunlight.
I see, because my follow-up question immediately would be, can this experiment be replicated with other plants, for example, especially in tropical places where either A, you get hit with typhoons or thunderstorms all the time, or number 2, you have a severe lacking of a product. Let's say we want to grow rice, and yet you still have issues of self-sufficiency because there's not enough rice, or if there's rice, then you have a lot of wastage in the process. So how can could this experiment be done in terms of, let's say we want to plant rice and then we put in solar panels on top so that we can see how much more rice can a hectare produce in the process?
Absolutely. So the question is whether or not this experiment can be replicated using other plants, essentially, and the different conditions of those plants. So unfortunately, this experiment wasn't actually experimental. It was a theoretical study. So what they did was they looked at the data from different solar farms, that covered a certain amount of area, and they calculated how much, with what efficiency, does the solar farm convert sunlight that hits that solar farm to electrical energy? How much electrical energy was captured? And then what they did was they just pieced together different studies that looked at, okay, what is the efficiency of converting that electrical energy into formate, this chemical from CO2? And then what is the efficiency that formate can be used to grow certain microbes? There's an energetic efficiency for growth. And then they pieced it all together, and they found the total efficiency going from solar panels to this microbial product. So this figure on the right isn't looking at any plants, it's imagining an area that's only exclusively covered by solar panels.
And does this also account for different topographies as well? Let's say, are we assuming that we're putting solar panels on top of relatively flat land, or can we account also for different topography wherein there may be different environments for growing, let's say rice or coffee or something like that? That would be a very interesting concept to look into.
No, it's fair. So one of the things with solar panels is that they, depending on the angle that you have the solar panels on or how you build them, they'll capture a certain number of photons. And the topography doesn't matter, right? If you build it along a mountain, it's going to be different amount of photons hitting it than flat surface. But these studies are often looking at what are the number of photons that hit the solar panels, and then how much electricity can we derive out of it. And so they're, I don't want to say they're independent of the topography, because that's not true. The topography does affect how many photons hit, but what they're looking at is given the topography of this area, how many photons hit and what's the efficiency downstream of things. So,
Sean, if you had to guess how long it will be until this technology is available, just technically, how long would it be also for it to be economically feasible?
Yeah, this is a fantastic question. One question is economic feasibility, and the second question is when it will be available. So I've talked with a couple of metabolic engineers, and what they've said is that for certain processes, these are already economically feasible. They're already more profitable than the best things that we have now. What's difficult, though, is getting companies to commit, large-scale companies, because there's many instances of things working very prettily in labs, and then when you transition to large-scale factories, there are all kinds of problems, and the company is really footing the risk of building these large-scale facilities. So, to answer your question, what I think is that economic feasibility for many processes are already theoretically, solid. The chances of us implementing these things relies much more on a company's willingness to commit resources into this. As an aside, one of the biggest issues, especially in the US, other countries I'm not as sure, is so committing to solar energy is actually power companies that are already ingrained. Oftentimes when you're talking about building these massive solar farms and massive solar panel installations, you're pushing out existing power companies. And so a lot of the issues with trying to implement these kinds of processes aren't even necessarily scientific. There are many scientific issues, don't get me wrong, right? There are many things that need to be solved, but one of the largest issues people are finding now is that the politics of pushing out these power companies who are ingrained into the economics of this country, that is the biggest hurdle right now to be faced. And so I wish I could tell you that in 10 years we'll be, eating purely electrically grown food, but I have doubts. Interestingly enough, though, DARPA has a project that they call Cornucopia, and it's exclusively about electrically grown food. It's a military-funded project. The military wants to be able to feed soldiers off of sunlight in foreign countries, and one of the missions is actually they hired a bunch of taste engineers. They want to grow microbes and then create jams, nutritionally balanced jams, and they want to make sure that they taste palatable enough that people can eat them. And so research is ongoing for this kind of thing, but whether or not we see it in any reasonable time frame, I'm not sure. Thank you.
So any other bites from power companies even who might want to venture into this? No, it sounds like not.
What was the question?
Not yet.
What was the question? Sean, will you repeat the question?
Sorry. Could you repeat the question?
Oh, sure. No, I just wondered if there were any bites from any power companies. We have Marin Clean Energy, which is, pretty advanced in terms of energy solutions. So I just wondered if there were, but it sounds like you're saying there were not.
Yeah.
So the military will be our leaders in this. Maybe.
Yeah, the U.S. is trying to highly incentivize this kind of work because they know that there's an economic grip.
Yeah, that's really good.
Yeah, it's nice. I'm sorry.
So on your graph, you've got the giant that shows energy production over time. You've got the giant growth of photovoltaic with a little teeny amount of storage.
Yeah.
And,
Oh, here we go. Yeah.
And we end up with photovoltaic out there as being about half, which is about the amount of time the sun shines.
Yeah. Yeah.
And so storage is can move some of that.
Yeah. So
How does this play in? How does the technology with biotechnology move into storage?
So it's funny that you mentioned that. I took this slide out, but the time that sunlight hits is actually almost exclusively anti-correlated with the energy usage in the US. People use energy in the morning, they use it at night when they get home from work, and that's exactly the opposite of how sunlight works. It peaks around noon, and then it dips around when people are getting home from work. And so when we talk about storage, people are like, if you start looking into solar panels, one of the biggest issues is that it doesn't seem like we're able to build enough storage to bridge that gap. That was actually one of the reasons why my professor was really interested in this kind of work. He said, we're not able to store all of that electricity, but what if we just used it? Well, the thing you can do once you generate the electricity is if you can use it fast enough, you can just generate gasoline, fuel, right? You can imagine there are different molecules that you can synthesize with that electrical energy, so that you don't have to store it, you're just continuously using it to generate something that can hold that energy better than a battery. And so, one of the things that we're trying to look into is, can we synthesize some other molecule that can serve as a quote unquote battery, right? Gasoline in this case would be a battery, ethanol would be a battery, and then you can use the energy later on. It's a great idea. Part of the issue is the speed, and I think that the speed of the process, and I think that will continue being an issue. I think that should be the focus, just synthesize things faster.
All right, Sean, thank you.